Hi guys, here's our next lesson, text and test 6, chapter 3.4. Topic today is Argand diagrams, which are, we've seen one already. The diagrams we use, it's the complex number equivalent of a number line. And as I said before, you get two number lines. You get the original number line called the real part, or the real axis, and then you get this imaginary axis going up here, which is because the imaginary numbers are a separate set of numbers. Your complex plane, which is what this is called, is a mix of real and imaginary. So it's very similar to coordinate geometry, which you've seen before, so it's not a hard thing to do. Plotting the number 2 on the complex plane just involves putting a dot down there. Question 5 on page 107, 108, which is where we're working today. We'll be doing these questions here. Question 5 asks you, if z is 1 plus 3i, plot each of the following complex numbers on an Argand diagram. Okay, so we're going to plot all these. They're written out here already. So 2, not hard to do. 2 plus z turns out to be 2 plus 1 plus 3i is z, so 2 plus 1 is 3 plus 3i. So 2 plus z is 3 plus 3i is going to be up here. Okay, and now I'm just going to show you what happened there when we added z. Is that the number 2 was shifted across 1 and up 3. Across 1, up 3. 3i is here. And the next one, 3i plus z, well that's 3i plus 1 plus 3i. That's going to be 1 plus 6i. 1 plus 6i is up here, and again I'll just show you what's happened. We've gone across 1, up 3. The next one is 1 plus I, which is this one here, and if you add z to that, 1 plus I plus z is 2 plus 4i. Okay, so hopefully we're seeing a pattern here. Across 1, up 3. The last two they asked you is minus 3 plus z, minus 3i plus z, which is going to be minus 3i plus 1 plus 3i. So it comes out as 1. That's here, starting, remember, from minus 3, and then you add z. There's that same across 1, up 3 pattern. Minus 2, minus 1, minus 1i is down here. Minus 2, minus 1 plus z turns out to be, well, minus 2 plus 1 is minus 1, and minus I plus 3i is 2i. So minus 1 plus 2i, which is up here. Okay, again, across 1, up 3, there's the effect. Okay, so the next part of question 5 asks specifically, what geometrical observation can be made about adding the same complex number z to other complex numbers? The answer is you get the same translation on the plane. Okay, adding z always causes the same translation. That's what we're seeing there, across 1, up 3 on the complex plane, or on the Argand diagram, whichever you prefer. Question 7 says find the modulus of each of the following complex numbers. Okay, well, a modulus we haven't talked about yet. So 5 plus 2i, 5 plus 2i is up here. The modulus is how far am I from the origin? It's not hard to answer. This is a Pythagoras question. If I've gone 5 across and 2 up, well, I've got a right angle triangle, 5 at the base, 2 at the side. Okay, so it's the square root of 5 squared plus 2 squared. That's going to be the square root of 29 is the modulus of that first number. Okay, that distance there is root 29. Second one, 4 minus 2i, so that's 4 minus 2i. That's the distance we're trying to find. Again, there's a right angle triangle there. Okay, 4 across, 2 down. So it's the square root of 4 squared plus, now I know there's a minus 2 there, but you can just go with the 2 squared. You can take the absolute value in every single one of these cases. So that's going to be 16 plus 4, it's the square root of 20. Here, minus 2 minus 4i, minus 2 minus 4i is down here. So again, that distance there, well, it's 2 across and 4 down. That's 2, that's 4. So it's just the square root. It's always just the square root of the first number squared plus the second number squared. That gets you the modulus. Okay, and you can take positives. If you like, you could say that that's minus 2 squared, which is still going to be plus 4 anyway. And that's minus 4 squared, which is still going to be 16 anyway. So we get root 20, which is the same modulus as up here. You'll notice because you got 4 and 2, 2 and 4, you're going to get the same answers. Which means these two numbers, in terms of complex numbers, we say kind of they have the same size, in inverted commas, that they're both the same distance from the origin. Okay, which means they have the same size. This and this number both have the same distance from the origin. Part 4 there, so again, square root of 3 squared plus 1 squared, and that's root 10. Okay, there's question 7. Question 9 asks us to evaluate the modulus of 3 complex numbers given just in busier form, but complex numbers nonetheless. So I'm just going to do part 1, evaluate the modulus of 3 plus I over minus 2 minus 3i. Well, the first thing you need to do is write that in simpler form. So you want to get rid of that complex denominator. Okay, you want to get a real denominator, so you multiply top and bottom by the conjugate, or the complex conjugate of minus 2 plus 3i, which is minus 2 minus 3i. Where does that get us? Well, 3 by minus 2 is minus 6, 3 by minus 3i is minus 9i, I by minus 2 is minus 2i, I by minus 3 is minus 3i squared, all divided by minus 2 by minus 2 is 4, minus 2 by minus 3i is plus 6i, 3i by minus 2 is minus 6i, and 3i by minus 3i is minus 9i squared. So we're going to get ourselves minus 6 minus 11i plus 3, because minus 3 by minus 1 is plus 3, all divided by 4, this disappears, that's 0, plus 9, okay, minus 9 by minus 1. So that's going to be minus 6 plus 3 is minus 3, minus 11i, all divided by 13. So that's the number we were looking at the start. So really they've asked us to find the modulus of minus 3 minus 11i over 13. Okay, and that's going to be the square root of minus 3 over 13 squared plus minus 11 over 13 squared. I'm going to finish this off down below, down here. That's going to be the square root of 9 over 169 plus 121 over 169. That's square root of 130 over 169, which is just, root 130 over 13. Okay. I don't think we can do much to take any square factors out of that. So there's our answer. We could have also just left that 13 out, found the modulus of that would have come out as root 130, and then put the 13 in at the end. But yeah, I mean, that's all there is to the modulus. It's just Pythagoras, like we see up here, applied to. Now, question 13, in the same exercise, asks us to investigate if z is equal to z bar, which you hopefully remember is the conjugate of z, for all z which are complex numbers. Okay, for all complex values of z. Well, z might be a plus bi. That's one way to express z. And if that's the case, then z bar is going to be a minus bi. Okay, well, the modulus of z is the square root of a squared plus b squared. okay, which is just root a squared plus b squared. And the square root of the modulus is the square root of a squared plus b squared. Well, that's also the square root of a squared plus b squared. So is it the case that the modulus of a number is always equal to the modulus of its conjugate? Yes, it is. Okay, so you'd see this in a Argand diagram fast enough. 1, 2, 3. Okay, so a number like 2 plus 3i and 2 minus 3i. These are conjugates, but the distance that they have from the origin is the same. Okay, they both have in their right angle triangle 2 across 3 up, 2 across 3 down. Okay, so the length of that hypotenuse, as it were, which represents the modulus, is the same. Okay, I would like you in class tomorrow, please. So classwork. If we can have a look on page 107, 108, question 2, question 4, question 6 is a very important one. Question 9, I'm going to ask you to finish off. Actually, I'll ask you to do question 8 and question 9. We'll have a look at question 14 and 15. Okay. See you tomorrow. Thank you.